Hello, good evening, everyone. This is Nikita, co founder and CEO of SSERD, an organization that is working towards space education and outreach for students, for university students, and in fact, the common public. We come up with a lot of initiatives which is working towards the goal of preparing the generation and know more about the space revolution that's happening. And SSRE Space Talk is one such initiative wherein we bring professionals from various space backgrounds and we let them share their knowledge with our community. They come from, we have had previous space talks wherein they came from space law background, space medicine background, entrepreneurship background, and a lot of astronomy and astrophysics background. Keeping that in mind, today we have one of the amazing speaker who again comes from astrophysics background. Before I introduce you to the speaker, as well as speaker to you all, let me also thank IAU Meet the Astronomer initiative, without whom we couldn't have had the speaker for the day. So this is a collaborative space talk by SSCID and IAU, wherein we bring an astronomer to speak to the whole community of SSCID. Now let me introduce you all. The speaker of the day is none other than Dr. Matthieu Renaud, who've been working for 15 years and more in the field of gamma ray astronomy through ground based and space based instruments, looking for the sources of galactic cosmic rays and nuclei. He's done all his high school and bachelor degree in physics in France. Going forward, a master's degree in astrophysics from Maiden University or Observatory from France. And then he also went on to do his PhD in high energy astrophysics at CEA on 44 titanium gamma ray lines in young supernova remnants with integral satellites. He also did his postdoc, and he was at postdoc position at MPIK, Heidelberg, Germany, on exploitation of Hess Techno telescope array data. And then he also did his postdoc at Kennes. And from 2010 to present, he's been on a permanent position at CNRS, affiliated to LUPM Institute, working on Fermi on Hess data towards supernova remnants and pulsar wind nebula on the development of CT observatory. That's amazing topics or like area of study in the field of astrophysics, I could say. And today we have Dr. Matthieu, who's going to speak to us all about cosmic rays, supernova, and their remnants. And now I hand over the screen to our speaker of the day. Dr. Matthieu, it's all yours.
Yes, thank you very much. Let me share my screen. It doesn't work anymore. I'm gonna have it. Isn't it?
Yes, you'll have to share your slide and put me aside.
Yes, but it doesn't work anymore. Let me try again. Excuse me.
You can just give me aside. Yes, you can move me aside from this band.
Now I see it. Okay, so let me try it again. Yep, here we are.
Perfect.
Okay, thank you very much for this introduction, and thanks for having me. Good afternoon, or good evening, or early evening, everyone. I'm very pleased to be here. And indeed, as it has been said, I'm going to talk about what I'm working on, namely cosmic rays, supernovae, and their remnants. And you already see in the background image 3 drawings or images showing you what we are going to talk about today. namely the cosmic rays on the left-hand side, a supernova remnant on top right, and one of those telescopes which allow us to probe these objects in the universe. So I'm going to start with a brief history, and it goes back into the early 20th century when physicists had noticed that their electroscopes were discharging even when sheltered from light in a closet. So electroscopes is basically this instrument that you see on the right, which allows one to measure the electric charges. And when we're putting that in a closet, the day after, it was discharged completely without doing anything. So they were wondering something is happening in the ambient air around them, something which is ionizing the medium in order for the electroscopes to get discharged. One of the most famous manifestation of ionization are the polar auroras, as you may know. But then some physicists decided to understand the origin of the discharge of the electroscopes. And one famous physicist was also a Jesuit prior, Theodore Wolff, decided to build by himself electrometers and bring them to the Eiffel Tower. He did many measurements at the foot of the Eiffel Tower and on top of the Eiffel Tower. At that time, we are in 1910. This monument was the highest ever built. And if you check the measure that you see in this table, it gives you actually somehow, let's say, the discharge rate of the electrometer. He was very careful with both how to build the instrument, the reliability of the instrument, but also how to make measurements. He was monitoring the temperature, the pressure, etc. And as you can see, 300 meters above sea level, the discharge rate was decreasing a bit, but not as much as expected if the origin of this ionizing radiation was coming entirely from the ground. So he was asking himself, is it really a telluric, terrestrial, or cosmic origin? But history remembers only one guy, usually, in sciences or in any field. And this is this guy, the Austrian physicist Victor Hess, who performed not less than 10 balloon flights between 1911 and 1913. He went up to above 5 kilometers in altitude with electrometers to measure, as a function of the altitude, to measure the discharge rate of the electroscopes. And to his surprise, he got this. You have, in terms of ionization power, or, as a function of the height, here are his measurements. After a kilometer, the rate of discharge of the electroscopes was increasing and reaching a factor of 4 or 5 at 5 kilometers in altitude. So he said, the results of the present observation seem most likely to be explained by the assumption that radiation of very high penetrating power enters from above into our atmosphere, and even in its lowest layers causes part of the ionization observed in closed vessels. With such a sentence that he wrote in several articles, he got the Nobel Prize in Physics 23 years after. And so what we know now, and I'm going to give you a very, very brief story of cosmic rays. It's very, very interesting study, a very interesting and rich history. But if you check just the milestones, the main dates, in it is a cosmic radiation. But the question still remained at that time in the 20s or so, is it due to photons or particles? What are we talking about? Okay, it comes from above. It is from the cosmos. But what is it? And so we discovered at the end of the 1920s that there was a latitude effect. So it means because of the Earth magnetic field that those so-called cosmic rays have an electric charge. So it can't be photons because photons are neutral. So it has to be particles. Even if Millikan was a great American physicist, was sure it was cosmic rays. Rays means photons. Actually, he was quite alone to think like this. Compton, and there has been a long controversy between the two physicists. Compton was sure, and he had shown that these cosmic rays have an electric charge. In 1932, Anderson discovered the positron, so the anti-electron in the cosmic ray radiation. In 1933, people discovered that there is not only a latitude effect, but also a longitude effect. And by demonstrating this, it proves that cosmic rays carry a positive charge. They have an electric charge, and it has to be positive. So it has to be not photons, but it has to be particles. And what is the most abundant particle in the universe? It's the nucleus of hydrogen atom. So it is proton. It has to be a proton. In 1934, those two astronomers called Bade and Zwicky suggested that supernovae are the main sources of those cosmic rays. We still nowadays keep this word of cosmic rays, even though they are cosmic, but they are not rays, they are particles. So keep that in mind. Cosmic rays are cosmic, but they are not rays, but we kept this historical naming. In 1938, Pierre Auger, a French physicist, discovered something very interesting, the so-called extensive air showers. Actually, when a primary cosmic rays hit the upper atmosphere, it generates millions, even trillions of secondary particles upon interacting with like nuclei of the atmosphere. And so only one particle with very, very high energy generate all of those particles, gamma rays, pions, protons, neutrons, electrons, positrons, muons, and neutrinos. And as I will show you briefly after, these extensive air showers are still used nowadays to reveal, to probe, to measure the highest energy cosmic rays. And to make a long story short, during like say in the 40s and 50s, early 50s, cosmic ray radiation has been the only mean for the physicists to discover new particles, pions, muons, kaon. Also heavy cosmic rays nuclei have been seen in a balloon flight at 30 kilometers in altitude. The great Fermi, Italian physicist Fermi, suggested a natural cosmic ray acceleration mechanism because we knew at that time that those particles have enormous energy, as I will show you just in a minute. And in the 50s, there has been a division among the cosmic ray physicists. Those who decided to move from high altitude laboratories to the first particle accelerators, looking for new particles. And these are called the particle physicists. But others decided to move from balloon flights to the early space exploration. We are in the early 50s and then in the 60s, and space exploration had already begun. And they were looking for now sources at the origin of the cosmic rays. So here is just to show you the first on the lower left image is one of the first particle accelerator, the so-called Cosmotron at Brookhaven, and of course the famous proton satellites launched by Russia in the 60s also, and who made those instruments. They had very precise measurements of cosmic rays, and it's quite a long story also, but a very interesting one. We were at that time, the Cold War between Russia and United States, but Russians were pretty advanced in space exploration and design of space telescopes. Anyway, let's move on to the 3 dimensions of cosmic rays. Let's talk about energy of those cosmic rays. What are we talking about in terms of energy? So here is the so-called spectrum of cosmic rays. So it's basically the flux of cosmic rays as a function of their energy. And look at this shape. It's a perfectly straight shape, a line, but of course it's in log in x and y. So it's it is called a power law. And look at the orders of magnitude in flux and in energy. We have like the so-called low energy cosmic rays on the upper left, but it's still giga electron volt. It's like a trillion of times higher in energy than the visible light. And look on the lower right, you reach 10 to the 20 eV electron volt. And here, it's the energy carried by one microscopic particle. And this energy corresponds to a tennis ball launched at over 100 kilometers per hour. So it's a macroscopic energy carried by a microscopic particle. And there is something in the universe which naturally generates those particles, which keep on arriving at Earth with a constant flux and showing you this spectrum. Look at where the LHC is. LHC is this instrument, it's like the largest particle accelerator humans have ever built. It's located under Geneva in Switzerland. And even nowadays, it barely reaches 10 to the 16 eV. We have natural processes in the universe which goes well above this energy, up to 10 to the 20, even almost 10 to the 21 eV. And we still don't know where it comes from, where all of those cosmic rays come from. So what we know, is that we have a power law spectra, which means a lot of low energy particles and very few high energy particles. We know that somewhere you have a galactic component. So there are sources in our own galaxy, the Milky Way, which generate those cosmic rays. And at the highest energies, it must come from other galaxies. And on the right, you see it's not only made of hydrogen nuclei, that is protons, but we also see helium, carbon, oxygen, neon, magnesium, silicium. It's ordinary matter. The only thing is that it's ordinary matter with extraordinary energy. To show you the mass distribution of those cosmic rays compared to the abundances of elements in the solar system, it's basically the same. You have a few differences here and there, but it's basically made of mostly protons, hydrogen nuclei, 90%, helium nuclei, 9%, and the rest is heavy nuclei, carbon, azote, oxygen, up to iron and even beyond, and a few electrons and positrons. Let me just go back. I'm not sure if you see the mouse here, but on the left, you see the proton cosmic ray spectrum, and you see that you also have some electrons and even fewer positrons. Let's remember this. Basically, 99% is protons and nuclei, and only just 1%, even less than 1%, are made of electrons and positrons. So what's about the spatial distribution of those cosmic rays? We talked about the spectral distribution, the energy distribution, the mass composition, and now what's about the spatial distribution? As I said, cosmic rays are charged, and mainly positively charged, except for electrons. But that means they are sensitive to magnetic field. And our galaxies is full of magnetic field. So a cosmic ray cannot travel in a straight line in our own galaxies. It goes like this. It sees its direction deflected constantly by the magnetic field. So you can't really make astronomy with those cosmic rays because it loses memory of its origin. I'm just showing you very quickly some simulations of a charged particle at a given energy in a constant B field. You know, it starts from a certain point and it goes completely crazy. So the arrival direction when you are on Earth doesn't point back to the origin where the source is, except at the highest energies, like 10 to the 20 eV or so, as you see here. Cosmic rays are less and less sensitive to B field, so they start traveling almost like a straight line, but only at the highest energies. One can do astronomy with those cosmic rays themselves. So what are the suspected cosmic ray sources? There are tons of them. We are dealing with very high energy particles coming from somewhere in the universe. So you really need violent, extremely energetic events in the universe, like massive stars explosions, compact objects, black hole, neutron stars, pulsars, magnetar, or even like the core of starburst galaxies, or even like the explosion of, say, rare types of massive stars, which lead to jets, like in gamma ray bursts. So I'm going to focus on only those supernova remnant, pulsars, and their nebulae. I'm going to talk mostly on supernova remnants, and I'm going to tell you what it is now. A supernova is this. At one day, you observe one galaxy like this one. I just picked one image like this. And the day after, the night after, you see this. A new star is appearing. Observationally speaking, it is what it is. This is what we now know as a supernova. But it's not a new star. It's the end of the life of a star. Another great example was this supernova, which occurred in 1994. It is as bright as the nucleus of a galaxy itself. At its brightest, it's very bright, but it's only due to one star, whereas the nucleus of a galaxy is made of millions of stars. So it's a very energetic event. Most of the time, astronomers are dealing with those supernovae. Most of them are quite distant, in distant galaxies, and usually it's more difficult to pick them up, like this example. But so astronomers really like to have classification of objects. So what we've done is to separate supernovae in two main observational classes. We call them types 1 and types 2. In types 1, you don't see any hydrogen lines in spectra, in optical spectra. Whereas in type 2, you see some hydrogen lines. This is one way to classify those supernovae. But it doesn't tell us yet what they are. Also, if you look at how their luminosity evolves with time, for the so-called types 1a, it's very homogeneous. Whereas for all the other types, type 2, type 1b, 1c, you have a great diversity in the so-called light curves. You know, like look at this one and compare to the other one here. Okay, so we decided to have this classification. It's still valid nowadays. It's a little bit more complicated than that, but it gives you the taste of the different classes and subclasses and subclasses of supernovae. But now, on the physics point, what we know nowadays is that we have two mechanisms. The so-called thermonuclear supernovae in red, which explain the type 1a's supernovae. And to explain all the others, it's called the gravitational core collapse supernovae. What it is. So for gravitational supernovae, it's the core collapse of a massive stars, more massive than 8 solar masses at the origin. It gives you a compact object in the end, either a neutron star or a black hole. You know, when a massive star is evolving in time, it moves from the helium burning phase to the hydrogen burning phase to the helium, carbon, neon, oxygen, and silicium burning phases. And at the end, it gives you an iron core which can get unstable, collapsed, and then trigger an explosion. This scenario has been put forward first by this guy, Hans Bethe. And for the thermonuclear scenario, to explain the type 1a supernova, we are dealing with a binary system with an accreting white dwarf. You know, a white dwarf is a very special object. It's one of the three compact objects, together with a neutron star and a black hole. And it has a specificity. It is completely unstable above 1.4 solar masses. And this has been shown by the great Chandrasekhar. I guess you all know him. And this is the scenario to explain type 1a supernovae. You have a white dwarf accreting matter from a stellar companion. It keeps on growing until it reaches the Chandrasekhar mass. It gets unstable and it explodes. In both cases, we are dealing with fantastic energies, kinetic energies of 10 to the 51 erg, temperatures which reach during the first moment after the explosion 10 to the 9 kelvins. And a shock is produced during the explosion, which travels at very high speeds, beyond, let's say, tens, thousands of kilometers per second. So we have a good candidate to explain cosmic rays. Again, cosmic rays are very high energy particles, so you really need energetical events like explosions of those stellar systems, either thermonuclear or gravitational. Nowadays, thanks to all of the computing facilities people have, in particular in our domain in Germany and in the United States, they are able nowadays, and it's like over the last few years only, they are able to make stars explode in computers. But of course, at the expense of millions of hours of heavy three-dimensional simulations. It's interesting because what they see And what those pictures show you is that a stellar explosion is never spherical. You have small and large scale instabilities which help the star explode. And so we put all the physical processes, equations into computers, and you run extremely extensive simulations to get those stars explode. On an observational side, I guess you see it. Here is what it looks like, what it should look like, what a supernova should look like. It's very bright during the first weeks, and then it's gradually fading until you see this bubble of hot ejecta of the star, which has exploded, expanding into the interstellar medium at larger speeds for thousands and thousands of years. And here you see, this is a montage video, but at the end you see this, it is a real image of the so-called Cassiopeia A supernova remnant in our galaxy. It was just to show you how it looks like in real life. Another great example, somewhere in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way. During the night of February the 24th, 1987, this star that you see here on the right, we are really in the center of the Large Magellanic Cloud. A star had just exploded. It was called SN 1987A, and it has a very specific place in our domain of research, because that was the last one we could see by naked eye, but also with some good facilities, even though they were not as performant as current facilities are. But still, we had neutrino telescopes, we had some space telescopes and ground-based telescopes. So we have been able for over 30 years to monitor the evolution of the supernova itself, and then to see the remnant itself appear in all the data, multi-wavelength data, radio, X-ray, submillimeter, millimeter, infrared, ultraviolet, X-ray, gamma rays. Nowadays, it looks like this, a bit over 30 years later. And here it is one of the youngest supernova remnant we know so far. Here's a collection of some other supernova remnants that one can see in our galaxy. All of them are galactic supernova remnants. Most of them, no, 5 out of 6 of them are from historical supernovae. They are so bright, those events, that when the star explodes, it can be seen by naked eye. And here you have on the upper left, you have, for example, the supernova remnant, which is the Tycho supernova remnant, named after Tycho Brahe, astronomer, who has monitored it when it was the supernova itself in 1572. And so all of those supernova remnants, as you may see, at the periphery of those hot bubbles, you see some delicate bluish line. These are the shocks I was talking about. And this is where, most likely, where high energy particles are produced, in those shocks of supernova remnants. This is the main theory we have nowadays, and we are testing that. So as I told you, just to go back to one point, due to galactic magnetic fields, cosmic rays wander in the interstellar medium, so their arrival direction does not point back to their origin. So how can we pinpoint potential sources of cosmic rays? The point is that during their production inside sources, during their escape from the sources, whatever they are. And during their propagation in the interstellar medium, those cosmic ray particles, mainly protons, but also electrons and nuclei, interact with everything, matter, photons, magnetic field, everything they find on their way. And during those interactions, they produce secondary neutral particles, mainly photons and gamma ray photons in particular, and high energy neutrinos. And those secondary particles are neutral, they are not charged, so they travel in straight line. And so now we can do some astronomy with those secondary particles to probe potential sources of those cosmic rays. And so I also told you that at the highest energies, cosmic rays travel almost in straight lines. So we have developed over the last 20 years the so-called domain of the astroparticles, namely those particles which somehow move in a straight line, like neutrinos, gamma rays, that means really gamma ray photons, and the ultra high energy cosmic rays, which basically are not deflected by magnetic field, not anymore, or just a little bit, in order to really produce images of the cosmos with neutrinos or gamma rays or ultra high energy cosmic rays to probe, to pinpoint, to see, to reveal the sources of those cosmic rays. I'm just would like to make a quick reminder of how the Milky Way looks like at different wavelengths, from radio waves to millimetric waves, infrared, visible light, X-rays, and gamma rays. And on the right, you see the scale is basically the energy of the electromagnetic light. So basically, more or less, visible light is like nearly electron volt scale. I'm going to talk about gamma ray astronomy, in which we detect GeV and TeV photons. So trillion and thousands of trillion higher in energies than the visible light. How do we make that? How do we perform gamma ray astronomy? First of all, traditional technologies at those energies, GeV, MEV, GeV, TeV energies, are useless. We cannot use mirrors really to directly detect gamma rays. We use methods from particle physics. In particular, to measure the energy of gamma rays, we use a calorimeter. And the direction of gamma ray photon is derived by calculation with computers. So we have some specific constraints in this domain. First of all, the fluxes are very, very weak. A single gamma ray photon carries a lot of energy, but you have just a few of them. So we are really and literally counting gamma rays, one after the other. The other constraint is that the atmosphere is opaque at those energies. So either you stay on the ground and you have to develop indirect methods to measure those gamma rays, or you go to space with the inherent constraints of space telescopes. You can't carry very, very large telescopes. The largest one is like 3 meters in diameter, HST, and soon the GWST with like, I don't remember the diameter of the dish, but it's more or less like 4 meters. While on the ground, you can develop telescopes as large as you want, more or less. So we have those constraints. Keep that in mind. Gamma ray astronomy is the youngest astronomy among all the others, among radio, infrared, optical, UV, X-rays. Gamma astronomy is the youngest one. I'm going to show you this. So I'm working on mainly two instruments. One is the space telescopes on board the Fermi satellite. It's been launched in 2008 from Cape Canaveral. It carries two main instruments. I'm not going to talk about the GBM that you see on the picture on the left, but I'm going to talk about this cube. This cube is really a telescope. It's a telescope. It doesn't look like a traditional telescope, but it is. What do we ask a telescope to do? To just measure the energy with a camera. You measure the energy of the light, and you measure its time, the arrival time, and its direction. This is exactly how the LAT does, the Large Area Telescope, but in the GV domain. It has a very broad field of view. It sees the entire sky in 3 hours, and it just do like a sky survey. It is composed of a trajectograph and a converter. The converter, and it's based on the pair production process. A gamma ray photon interacts with the matter inside the LAT telescope, and it produces an electron-positron pair. This pair propagates into the telescope until it reaches the calorimeter, where the entire energy is measured. From the trajectory of this pair and the energy measured in the calorimeter, we can reconstruct the energy and the direction of the incident gamma ray photon. Let me briefly show you in a nutshell the main results of the Fermi LAT telescope. It has a modest angular resolution. This is what you see here. Its angular resolution is just like 30 arc minutes at GeVs. You see, with just a very modest optical telescope, you reach like orders of magnitude better. Already with our own eyes, we reach angular resolution of about 1 arc minute. But as I told you, gamma ray astronomy has a lot of constraints, technical and natural constraints, and it is very young, still quite young. I'm going to show you also for the TV astronomy how young it is. But so now Fermi really revolutionized the field. The latest catalog, which has been published just by the end of last year, from the first 10 years of data, contains almost 6,000 sources, among which 1/3 is still unidentified. If you don't believe me that you have 6,000 sources in this sky map, of course you have to develop a lot of computing softwares to pick up all of those sources. And as you may see in the legend, we have among those sources almost 50 supernova remnants shining at GeV gamma rays. And here they are. I'm just showing you a few of them: CAST A, W51C, W44, IC443, all of those very poetic names of galactic supernova remnants seen at GeV energy, but it tells you there are some high energy particles in those supernova remnants which are emitting gamma ray photons. Good. What's about HESS? HESS is the other telescope array. It's a telescope array on which I'm working. It's ground-based telescope, 5 telescopes located in Center, Namibia. It's been working since almost 20 years. Namibia is a very ideal situation to observe the central regions of the galaxy. It has an unprecedented sensitivity at TV energies, lots of discoveries, and let me just briefly, I'm about to finish in about 5 minutes, but I would like to show you how it works. A gamma ray photon also interacts in the upper atmosphere, and it also triggers an atmospheric air shower. That means all of those secondary particles, and those secondary particles travel at a speed which is larger than the speed of light in the air. And because of that, all of those secondary particles trigger or emit Cherenkov light. It lasts only 5 nanoseconds. So you really need to have very fast electronics of all the cameras. But what is interesting in those telescopes is that they work like an array. So each of those telescopes sees the Cherenkov light under different angles. So you can reconstruct the origin of the direction of the incident gamma ray photon. And to show you how young is this astronomy, the TV astronomy, the first ever detected source, celestial sources at TV energies, dates back 1989 only. And nowadays, thanks to Hess and other similar Cherenkov telescopes, we have reached like over 200 sources, both in our galaxy and also extragalactic sources. In particular, Hess has been able to perform a galactic plane survey of the inner part of the Milky Way from 2004 to 2013 to reveal over 70 sources in the plane. So it is basically the same image as before, but just I cut into pieces the galactic plane. And it has a better resolution than Fermi, 5 arc-minute at TV energies. And you see all of those sources. Among them, we still have nearly half of them, which we don't know what they are. But as you also see, we have revealed for the first time at TV energies 8 supernova remnants with some very specific, and it took us quite some time to develop all of those softwares to identify supernova remnants. But here they are, 8 of them. And we also have 2 supernova remnant candidates. This guy and this guy here, we are not sure if they are bona fide supernova remnants, but all the others are. And again, if you see TV gamma rays, that means that you have at least TV cosmic rays or at least TV particles inside those sources, those particles which are currently which are being accelerated by the shocks of those supernova remnants. And this is certainly the main sources of galactic cosmic rays. Let me show you 4 of those supernova remnants. We see them in X-rays, in TV gamma rays. They look similar at both wavelengths, at both energies. But the main point is that the gamma ray emission may come from, we don't know if the gamma ray emission comes from electrons or protons. Electrons, cosmic ray electrons, high energy electrons, do emit gamma rays like almost exactly like cosmic ray protons. So the main point is that those gamma rays, those gamma ray images do not tell you if they are due to electrons or protons. But remember, in cosmic rays, 99% are protons or nuclei, and only 1% are electrons. So if those gamma ray photons come from electrons, well, maybe those supernova remnants are the main sources of galactic cosmic ray electrons, but it's only 1%. It doesn't tell you much what's about the other 99%. But we may have some parts in those supernova remnants which are due to cosmic ray protons. And this is exactly what we deal with, and it's a long story again, but I think I'm running a little bit out of time. And I would like just to finish by mentioning that cosmic rays, of course, I'm just presented to you the specific domain of research in high energy astrophysics. And in this domain, the nature of the sources at the origin of cosmic rays is still unknown. We have all of those extremely energetic and violent events and sources in the universe, which are still the main suspects. We think that upcoming gamma ray observations will clearly tell us what are the main galactic cosmic ray sources, in particular with the so-called Cherenkov telescope array, which is being built in two sites, one in northern hemisphere and the other one in the southern hemisphere in Chile. And we have performed some simulations, and this is how the galactic plane survey, the galactic plane of our galaxy, of the Milky Way, could look like in a few years from now. Full of sources, not just like 70 or 100, but maybe 1,000 or so. And all of those sources, in those sources, we may find which are those at the origin of the galactic cosmic rays. But I say cosmic rays is not only just for astronomers or high-energy astrophysicists. We know that cosmic rays are a major component in the interstellar medium. They operate in chemical reactions through the production of free radicals. And so we now know that in the interstellar medium, there is a very rich chemistry ongoing. And cosmic rays is an important ingredient to explain the rich chemistry ongoing in the interstellar medium. Cosmic rays can also affect, because of their ionizing power, this is how we discovered them more than a century ago. Because of that, they can affect biological cells through DNA damage and mitochondria dysregulation. It is called an aging-like effect that people can experience during space flights. So it has to be accounted for, it has to be taken into account when we talk about space exploration, like going on Mars, you know. Also, radioactive, the carbon-14, which is used to date archaeological and geological samples, this entirely arises from the interaction of cosmic rays with nitrogen in the atmosphere. Without cosmic rays, no carbon-14. So it is used also in other domains of research. And also, I didn't talk much about those particles, the muons, which is one of those secondary particles in these extensive air shower triggered by cosmic rays. Those muons have a very penetrating power, and they really can reach ground. And they are used to perform tomography of large volumes, natural or man-made volumes like volcanoes and pyramids. So I think I'm done. I just leave you with a few references. You'll find easily the official websites of Hess, Fermi, and CTA telescopes experiments, but also about supernovae and supernova remnants. I really like those two books, one from David Arnott and the other one from Stevenson and Green. Okay, so thank you very much. Let me go back to Skype and stop sharing.
Thank you so much, Dr. Matthieu. It was amazing set of information that we could gather today from your space talk. We have pretty amazing questions as well from all our audience. So everyone was there watching live on YouTube. If you have any questions, do put it down. But I've already collected a few set of questions, and these questions are again like like it's mind blowing for me. And all these are asked by the students who are in their 17, 20, right? They're like pretty young. So, Dr. Mathur, the first question for you goes like this.
Yep.
How do galaxies act as accelerators for cosmic rays?
Okay, that's a good question. It is not part of my specialty, but let's say, as I told you, cosmic rays, you have a galactic component and you also have an extragalactic component. For the extragalactic component, we think that maybe the cores of galaxies can accelerate those cosmic ray particles. Not the galaxies as themselves. So we think that really at the center of every galaxy, we have a supermassive black hole. Million or even trillion of solar masses. There, they are creating processes of matter which gets very hot at extremely high temperatures. But because of magnetic field, we think that also jets are triggered. And in those jets, which are very, very powerful events, ultra high energy cosmic rays can be accelerated. So this is one usual suspect to explain the highest energy cosmic rays, the cores of the galaxies.
Great. Thank you so much. Niranjan, I hope that answered your question. We have another question which goes like this. Can we store cosmic rays to use it at different fields?
To store them. We can store them, but if the question is what could we do with this energy storage, I guess it's more or less the question that one could ask. I would say I did the calculation a few years back, but I don't remember the numbers. But in terms of the total energy that goes into Earth, say, it's very few. It's much less than solar energy, for example, but like orders of magnitude lower. Even though we are dealing with the particles with the highest energies that we couldn't imagine a century ago to have this, they are very few in numbers. So if you somehow multiply the density of energy by the number of particles, then you end up with like a very, very moderate total energy. So we could store them. This is actually how a cosmic ray telescope works. It somehow stores the energy of the cosmic rays in order to detect it and to tell here is a cosmic ray. So we can do that, but in terms of total energy, it's not much.
Okay, thank you very much. We have a question from YouTube live chat.
Yeah.
How can we differentiate between the nebula and the remnant matter of supernovae? Because they both look very similar.
This is an excellent question, and this is why I still have a job and I'm still paid, because it's not easy. If it was easy, I wouldn't work anymore in this field. No, that's a very good question. And let's say, what makes a difference between a supernova remnant and a traditional nebula? If you think a nebula as an H2 region, for example, the two share many similarities, like they can be shell-like, morphologically speaking. But a supernova remnant emits non-thermal emission, whereas H2 region is thermal. And so you really need to combine multi-wavelength observations from radio, millimetric, infrared, up to gamma rays to really distinguish between the two. But it's still delicate, and again, because of the moderate angular resolutions of gamma ray telescopes, as you may have felt in the images I showed you, we have a poor, let's say still poor, relatively poor angular resolution. So we don't really have a clear morphological measure of those TV or GV sources. And this is also one constraint to identify them as supernova remnant or anything else. It is another difficulty for us. So it's a good question. I mean, it's not an easy part of our work. Yeah.
Thank you so much. We'll have last two questions. Among them, the next question you have is how do we how we would protect humanity by cosmic rays if we settle down on Mars?
How would, excuse me, can you repeat the question? How
Yeah.
would we
How
protect ourselves?
yes, from cosmic
Uh,
rays if we settle down on Mars.
oh yeah, but the answer is there is no possibility to. Cosmic rays are coming from everywhere. As I told you, we're still looking for the main sources, but this is like a kind of fundamental and very specific question, which we like as researchers in astronomy. But say it's a natural process. Everywhere you'll find cosmic rays. Mars has not anymore an atmosphere, or it is very tiny, very thin, very rare, tenuous. So maybe by building a cosmic ray umbrella when we'll get on Mars, I don't see any other option to get protected from the galactic cosmic rays. But this is a real question. Huh? I think we are stuck to stay on our nice and warm and delicate planet.
Agree. I totally agree. It's a very beautiful planet that we all are living in, and we need to make sure we keep it in the same way how we got it. Coming
Exactly.
to the
Or even better, I would say,
even
for the
better,
next
making
generation
better.
of people. Yeah.
True. That is so
Mm.
true. So here is the last question. Um, what is your vision for the future in the sector of astronomy, and what is that you would like to do? At the same time, there are so many audience over here who are watching who wants to become an astronomer, astrophysicist. What is that small tip that you would like to give them?
It's a vast question because, well, let's say I'm going to share my own experience. I like doing research in astronomy. It, of course, it's what is called long study process. But anyway, it's a and I do remember as the time goes that I like astronomy because it tells me something about our own position, our own like as we said just before regarding space exploration and Mars landing, putting some humans on Mars. What does it mean in terms of what? In terms of energy consumption, in terms of how much it costs to do this, and what's for? I guess somehow I now have a kind of a reversed view of what it means to be on Earth. And one thing, my vision for astronomy is like, of course, we cannot stop developing instruments. We cannot, let's say, we could mitigate a little bit how it goes, but say, in particular for space exploration, for space, the use how is it called? This guy, Elon Musk, you know, he's about to launch like tens of thousands of satellites. And we know that it will make some difficulties in keeping on doing astronomy. So we have all of those questions, but it's exactly the same for the climate change. This is always the same kind of questions. Do we keep on developing technological aspects and keep on moving like this without thinking or looking a little bit aside and try to make things a little bit more better? And I think my vision as a modest astronomer, which is like purely like my questions are like just about fundamental aspects of physics. But still, you are using instruments. What's the cost of doing this? And so I like this part this is one part of my answer. The other part, to make it shorter, is education. Like, it's important, I think, for everyone to get a feeling of a natural environment, which is the starry sky. And we are losing it nowadays because of light pollution. And so I'm quite involved now in those two questions. Say, what it means to make astronomy and what is the cost and what's for, and also education to astronomy for everyone, and in particular for kids, with an emphasis on light pollution. This is how I think astronomy should move on. Keep on doing research, and that's one important aspect, but not only this. I'm paid to do research, but I think it's better and to get paid to also share.
No, we respect your job because because I know that all the astrophysicists or all the scientific community, you all go one step forward than everyone, and you show that dedication and show us what's there in the world along with us, right? So thank you so much for answering all the questions, at the same
Thank you very
time
much.
spending your Sunday time with us by giving a talk. And it was wonderful, very informative, and I could see all our students with so much of questions and a lot of things running in their minds, and that's what we want. And I think we've been successful, and you made it possible. So a very huge thanks from all the audience, in fact, the whole SSERD team. Thank you very much, Dr. Matthieu.
Thank you very much. And I see that you would like to stay back on the call after I say good. Okay, that's fine.
So,
Thank you very
audience,
much.
thank you very much. And we will be back with another amazing space talk very soon. So, kindly keep waiting. Until then, follow us on social media and particularly on YouTube. Give it a like, share, and do subscribe. And we will be back with another space talk and a lot more programs. Thank you very much. Bye bye.